Alright, so in this video, uh, I will explain this equation, the equation of conservation of energy, uh, in a simple way using an analogy with money. Now, there are several reasons why money is a good analogy for energy. One reason is because just like energy, money manifests itself in various forms. So just consider $100, right? So $100 could be manifested as a $100 bill, two $50 bills, basically cash. But it could also be manifested in ways which are not cash. So it could be $100 on a gift card. It could be $100 in a prepaid debit card. It could be stocks valued at $100. It could be $100, $100 balance in your savings account, and so on. So there's multiple ways in which $100 can be manifested. And same is true for energy. So energy, 100 joules of energy could be 100 joules of kinetic energy, it could be 100 joules of potential energy, it could be 100 joules of heat energy, 100 joules of light energy. So 100 joules of chemical energy in your food. For food, energy is usually measured in calories, but that's just another unit of energy. So 100 joules or a certain amount of energy could be manifested in a multiple different forms, a variety of different forms. So that is one analogy, one similarity between money and energy. Another interesting similarity is that we know that money cannot just materialize out of nowhere or disappear. So money always has to be accounted for, right? Um, Same thing with energy. Energy cannot just manifest out of nowhere, and energy cannot just disappear. It always has to be accounted for. So that is called the conservation of energy. So that is what I'm going to show you right now. So you can understand this equation of conservation of energy very easily if you just consider um the analogy with money. So kinetic energy would be analogous to uh, money that you have in your wallet, ready to use in your purse or your wallet. So that would be kinetic energy, right? Potential energy, that would be analogous to money in your bank. So potential energy is not ready to use right now, but you can always withdraw it from your bank and then use it, which means you're converting potential energy into kinetic energy. All right, now what about mechanical energy? So EMEC, uh, the definition of EMEC is K plus U. And the analogy for that would be it's the amount of money that you have on your wallet and in your bank. So it would just be your net worth. Let's just assume that these are the only two types of money that you have, two types of wealth that you have right now. So this would be your net worth. Okay. Now there are different types of work, right? So W other stands for the work done by non-conservative forces, by external forces, and non-conservative forces, as we've discussed in class. So what does W external stand for in our analogy over here? So remember that work represents the transfer of energy into or out of a system, right? So W external means the energy that's transferred by an agent out external to the system, by some external agent. So in our analogy, it would be money received by you from someone or paid to someone. All right. What about W non-conservative? Now, one thing we know about work done against non-conservative forces is that once you do work against a non-conservative force, you can never recover that energy. So to make an analogy with money, that would be like an expense. Like suppose you go out to Chipotle and buy a burrito and eat it. So now the money that you spent on that burrito is just gone, right? There's no way you can get it back anymore. So this would be analogous to an expense. All right. Okay. And what about work done by a conservative force? So the work done by a conservative force is um, is a transfer between your wallet and your bank. So if you take money out of your wallet and put it in your bank, or if you take money out of your bank and put it in your wallet, so that kind of transfer would be the analog of the work done by a conservative force. And these forces, you know that conservative forces don't change your total mechanical energy. So that's also true in our analogy. If you take money out of your wallet and put it in the bank, or vice versa, you are not changing your net worth. The sum of k plus u remains the same, right? All right. So now with this analogy in mind, let's try to understand our equation here. So we have k plus u plus w external plus w non-conservative. I'm just writing out the w other, and these are initial, is equal to k final plus u final. So this is your net worth, right? And so this quantity k plus u represents your net worth that is at a given time. So your initial net worth uh, plus all the money that you've received from external agents or paid to external agents, plus all the money that you've spent um, in expenses has to equal your final net worth, right? So it's as simple as that. So that is why this equation has to be true. It's just basically accounting for energy. Now, one thing you'll see from here is that suppose W external is equal to 0, and the only forces that are acting on the system are non-conservative forces, right? So what's going to happen to the total mechanical energy? So what happens to, actually let's just do another case. So suppose W external is equal to 0 and W NC is also equal to 0. So what happens to the net worth? So you're not receiving money from anyone or giving money to anyone. You're not spending any money on expenses. So your net worth will remain the same. There might be conservative forces. So WC is not necessarily 0. So in that case, your net worth will not be affected. So if the only forces that are operating on the system are conservative forces, um, your net worth will not be affected. Why? Because conservative forces just transfer energy from kinetic to potential or from potential to kinetic. So they don't really change the total mechanical energy, right? In fact, that's the whole reason they're called conservative, because they conserve the total mechanical energy. So if the external forces are 0 and the non-conservative forces are 0, and the work done by conservative forces is not necessarily 0, then E mech will remain, k plus u will remain conserved, which means that its value will remain unchanged. What if, let's look at another case. What if W external is 0 and W non-conservative is not 0? So there are some non-conservative forces acting on the system. What can you tell me about k plus u? So will it go up or will it go down? Think about that for a moment. Feel free to pause the video. So if W external is 0 but W non-conservative is not 0, what's going to happen to k plus u? The answer is, let me just write the question and the answer. What happens to k plus u? The answer is k plus u will decrease. How do I know it will decrease? That is because if the only forces that are acting are non-conservative forces, remember that non-conservative forces like friction always do negative work. They always remove energy from the system. So if the only forces that are operating are non-conservative forces, the kinetic energy, the sum of kinetic and potential energy will decrease. So if using our analogy, so suppose somebody has a certain net worth, right? And they don't receive money from anyone or pay money to anyone, but they do spend a lot of money on frivolous expenses, like they're buying Skittles and candy and sodas all the time. Um, what do you think will happen to their net worth? The answer is it will go down, right? Okay, and right, and a similar question, which should be pretty obvious now. Suppose W non-conservative is 0, but W external is not 0. What's going to happen to K plus U in this case? The answer is K plus U will either increase or decrease depending on the sign of W external. So if W external is positive, that means the external force is supplying energy to the system. That would increase the total energy budget of the system, K plus U. If W external is negative, that means the external agent is taking energy away from the system, and so K plus U will decrease. And to continue our silly analogy here, it's like somebody has a certain amount of certain amount of money, and they receive some money from a relative. That would be an example of external force supplying energy into the system, so their net worth will go up. Or they might receive a library fine, in which case they have to pay money to the library, and their net worth will go down. All right.